Okay, so good afternoon to all and welcome to lecture number 25. Today we'll study about this one, response of first order system. So in yesterday's talk we talked about standard test signals and then their relations and so on. And also we talked about something about the time response, time response and so on, right? So okay, so you know that order of the system is nothing but the highest power of the denominator of S. So that is nothing but the order of the system, and type of the system is nothing but what is the highest power of common S in the denominator. So that is nothing but the type of the system, and that type of the system determines how many poles are there at the origin. Okay, now here see, we are talking about the first order system. So here the highest power of S in the denominator is 1. So that's why it is called as the first order system. Okay. Now, where yesterday we have studied this one, where K is nothing but the DC gain, and then this time T is nothing but the time constant of that system. If time constant of the system is large, then that system will be sluggish for step input and so on. And we'll see, okay, how the value, if you change the value, first thing is that we'll see how to calculate the response of the system for impulse input, as well as how to find out the response of this system for step input. And thus, then once you get the response of that one, what is the effect of changing the gain of the system, as well as what is the effect of changing the time constant of that system. So that we are going to study in our today's lecture. So here, see that here the denominator is written in 1 plus S form. Okay, if it is not written in 1 plus S form, then you have to write that one, and then whatever you get the coefficient of S, that is nothing but the time constant. So yesterday we have studied the two problems, and then we have found what is the system gain and what is the time constant of that system and so on. So time constant is basically a measure of how quickly a first order system responds to the unit step. Means when you apply a unit step input to that system, how quickly that system reaches to the reference value. So that is decided by the time constant. So as I said that if time constant is small, then system will respond very quickly, and if it is large, then that system will respond a bit late. Or that system will be a sluggish system and so on, right? So basically, time constant is a measure of how quickly a first order system responds to a unit step and so on. And the DC gain of the system is the ratio between the input signal and the steady state value of the output. So that is decided. So we'll see the effect of changing the time constant as well as effect of changing the gain on the response of first order system. Okay. Now, yesterday we have studied this one, like, okay, so here this example we have taken, like for example, the transfer function of that system is z of s is equal to 10 by 3s plus 1. So here gain is 10 and time constant is 3 seconds. Also, we have taken this problem yesterday that for this system, find out the time constant and system gain. So directly you cannot tell, because you have to make this in 1 plus S form. So for making this 1 plus S form, you have to divide the numerator and denominator by 5. So your system gain will be 3 by 5 and time constant will be 1 by 5. So this will be, because after making this 1 plus S form, this coefficient will be 1 by 5, and that is nothing but the time constant. And this will be a DC gain, which is equal to 3 by 5. I hope that you have understood yesterday how to find out the gain and time constant of the first order system and so on. Now, in this lecture, we are going to study response of the system for two input. One is basically, see, first order system. First input is your impulse input. What is the response of that system? Then after that, we'll change the input from impulse to step input, and we'll see what is the response of that system. And then after that, if we change the value of time constant, how that system will behave, and if we change the value of DC gain, how that system will behave, and so on. So that is what we are going to study in our today's lecture. Now see that this is the first order system. Why it is called as the first order system? Because the power of S is 1. Okay, and then see the overall transfer function is given by K divided by Ts plus 1, where K is the DC gain and T is nothing but the time constant of that system. Now here we are talking about impulse response of the first order system. Means here R of S means your input is impulse and output we have to measure. The response we have to find out the response, means we have to find out the value of C of T in time domain. So this is in frequency domain, basically R of S, or in Laplace domain. Now you know that what is the Laplace transform of unit impulse? Can somebody tell me? See, when you are applying the impulse as an input, what is the Laplace transform unit impulse? Am I audible to you people?
Sir, A.
Yes, sir.
A, okay, or if A is equal to 1, then that will be 1, right?
Yes.
Now, what is the C of S by R of S of this system?
Transfer function.
So that is equal to transfer function. What is that?
K by Ts plus 1.
K by Ts plus 1, right? C of S by R of S is K by T of S plus 1. Now R of S impulse, that is the Laplace transform impulse response, is 1 unit. We are talking about unit impulse. So if you take Cs by R of S is equal to K by T of S plus 1. So if you take R of S to the right side, so C of S will be equal to K divided by T of S plus 1 into R of S. Now value of R of S is 1, so you can find out the value of C of T, right? So here your unit impulse response is having magnitude equal to 1, is it will be having magnitude equal to 1 when T is equal to 0, and rest of the time this is its magnitude is 0. So this is unit impulse signal. Now this is applied as an input, and we'd like to find out what is the response of this system, right? How that system behaves with respect to time, that we'd like to find out. Now see, R of S is nothing but the unit impulse signal, that is delta of S, which is equal to 1, and C of S by R of S is equal to K divided by T of S plus 1. So C of S will be equal to K divided by T of S plus 1 into R of S. Now R of S is 1, so this C of S equation will be basically K divided by T of S plus 1. Now can you take the can you find out the value of C of S here? How to find out the value of C of T from given? By taking Laplace transform, inverse Laplace transform of this equation, we'll get the value of C of T now.
Yes.
Okay, so if you take the inverse Laplace transform of this one, so what will be the inverse Laplace transform? So this is in standard format. Okay, K divided by this one, Ts plus 1. So what will be this one? I hope that you know that the 1 upon S plus A, inverse Laplace transform of 1 upon S plus A is what? What is the inverse Laplace transform 1 upon S plus A? Can somebody tell me what is the inverse Laplace transform of 1 by S plus A? It is e raised to minus 80. Yeah, it is e raised to minus 80. So see that C of S is this one. So what we have done here, again we have made in S plus A form. So this A is nothing but 1 by T, and then this is the constant. So what? Okay, if you take the inverse Laplace transform of this one, what you will get? So this will be constant as a K by T, and this is 1 by S plus 1 by T. So what will be that?
E raised to the power minus T by T.
Right, minus T by T. Okay. So in order to compute the response of system, In time domain, we need to compute the inverse Laplace transform above equation. So this will be, we are going to take, see that this is the Laplace transform of this equation, this standard formula. We know that inverse Laplace transform C by S plus A is nothing but C into e raised to minus at. So C is constant basically, and then this 1 by S plus A is nothing but e raised to minus at. So same format is there. So it will be K by T, K by capital T into e raised to minus what? Whatever is this one, this minus. So minus t by small t by t. So this will be equal to K by T. So its inverse Laplace transform is C of t is equal to K by T into e raised to minus t by t. I hope that you have understood this one.
Yes, sir.
Okay.
Yes, sir.
Now, can you tell me what is the value of C of t when t is equal to 0 from this one, small t, time t equal to 0?
K by T.
Okay, if t by, okay, means basically if t is equal to 0, you will get the K by T, and if t is equal to infinity,
So it will be
yes,
0.
okay. Now, whether that system is stable? See what stability means. Basically, when input is applied, okay, if there is no input, your output should should be 0, na? In the absence of input, output should be 0. If there is an input, now when input is there here, input is there at t, okay, basically at t equal to 0. But rest of the time, see that if you look at this one, your input is there at t equal to 0. For rest of the time, there is no input. Means you should get output only at t equal to 0. Rest of the time, as t approaches to infinity, it should, your output should basically reach to 0 value. So see that with this equation, definitely when t tends to infinity, small t tends to infinity, it will reach to 0. And when t is equal to 0, at that time you got this as a K by T. So your output is K by T, capital T. And then as t tends to infinity, it will reach to 0, means this system is stable system, right? So first order system with this this one, impulse response or impulse input is a stable system, right? Now, see that if value of k is equal to 3 and if t is equal to 2 seconds, okay, if you take time constant as a 2 second and again as a 3, so what will be basically the response of this system? See that K by T means basically K is equal to 3 and T is equal to 2. So when T is equal to 0, at that time, this will be K by T. So K by T is what? K by T is 3 by 2. 3 by 2 means 1.5. So your response will be 1.5. And as T goes on increasing to the infinity value, so it will reach to 0 value. So if such response is there for this system, then that system is said to be a stable system, because when there is an input, so input is available at t equal to 0, so you are getting the output. But if there is no input available, then your output is tending to 0. So we can conclude that this system is a stable system, right? I hope that you have understood this one.
Yes.
Okay. Now, we will see the next response of the system, that is step response of first order system. Now, same system is there. Only thing is that we are changing the input. So earlier we took the RFS as an impulse input. Now here we'll change from impulse to step input. So you know that step input, this one, Laplace transform of step input is 1 by S. Laplace transform for impulse, unit impulse input is 1. Laplace transform unit step is 1 by S. Laplace transform ramp input is unit ramp is 1 by S square, and Laplace transform of unit parabolic input is 1 by S cube. So here we have changed from impulse to step input. So R of S is equal to 1 by S. Now we'd like to find out the response of this system for this input. So means what we would like to find? We'd like to find out the value of C of t for unit step input. Now you know that we'll solve this problem similarly, whatever we have done in the last this one. So you know that C of S is equal to what? C of S by R of S is what? K upon T of S plus 1. Now what you have done is R of S is taken here. So R of S is 1 by S. So that's why this C of S will become K upon S into T of S, Ts plus 1. I hope that you have understood this one up to this point.
Yes, sir.
Okay. Now we have to make the factor of this, and then we have to take the inverse Laplace transform so that we will get the value of C of T. So in order to find out the inverse Laplace transform of above equation, we need to break into the partial fraction expansion. Okay, and this partial fraction expansion will be of this one will be K by S minus KT divided by Ts plus 1. Now, can you find out the inverse Laplace transform or C of T from this one after partial fraction?
Yes, sir.
Okay, I think you can take the value of K common. Okay, so if you take the K common, what will be the response? C of T. Can somebody tell me?
Sir, 1 minus e to the
Right.
power
Right.
minus small t by capital T.
Very good. Very good. And K is common, right?
Yes.
Yeah. So here your response will be equal to K into U of T minus e raised to minus T by T. So here unit step is nothing but value magnitude equal to 1. So this will be 1 minus e raised to minus T by T, capital T, right? So where U of T equal to 1. So C of T will be equal to K into 1 minus e raised to minus T by capital T, right? Now, just we'd like to plot the response of this system for unit step. Okay, so how to plot the response of this system with respect to time response of the system? So you have to change the value of t right from 0 to infinity, and then if you know the value of capital T and if you know the value of K, then you can easily plot the response of this system, right? So like for example, when t is equal to t, like for example, if this t and this t is same, then this C of t will be equal to K into 1 minus e raised to minus 1, because this if t is equal to t, this will be e raised to minus 1, and then at that time C of t will be equal to 0.632 K. So it will depend only on the value of K. If time constant and then this time is same, at that time this value will be same. Now see that if K is equal to 10 and t of t is 1.5 second, then see that if value of t, small t is 0, okay, if small t is 0, what will be this term?
0.
0. So 1 minus 0 will be what? 1 minus 1 will be, oh no, if value of t is equal to 0, so what will be this value? It will be 1, na? It will be 1. So 1 minus 1 will be 0. So your first point will be 0, right? Now, I hope that you have understood the first point.
Yes, sir.
See, just you have to put the value of t equal to 0. If e raised to minus 0 is nothing but 1. So 1 minus 1 is 0. So anything multiplied by 0 is 0. So your response will be C of t will be 0, right? Now what is your input? Input you have applied basically 1. Okay, unit step input you have applied. Now as small t goes on increasing, see, this is your x-axis is small t, and this is nothing but your response C of t. So we are plotting this C of t with respect to time. Now when time is equal to 0, your response is 0. As time t is equal to capital T or time constant, or t is equal to 1.5 second, at that time this response will reach to 63% of its value. Now what is this value? Basically 10, up to 10 now. This gain is 10. So as you go on increasing the value of t, you know the value of capital T, and okay, you are taking the value of discrete value of small t time as a 2 second, 3 second, 4 second, 5 second, 6 second, like that. So your response of that system will be like this. So it is reaching to the desired value after some time, right? I hope that you have understood this response of first order system for the step input. Yes, please. If you have any doubt, you can ask here. Just you have to see, you know the value of k, you know the value of time constant, and then this small t is nothing but the time. So we have taken time on x-axis whose value is 1 second, 2 second, 3 second, 4 second, 5 second, and so on. So for various values of small t, if you put the small t value and you know the value of capital T and K, so from that you will get all those values, and just you have to plot the graph. So this graph you will get like this. So when equal to it is 10, or like for example from 7 itself, it will reach to 10 value or close to 10 value, and so on. And your steady state output will be equal to what? When k, at infinity, what will be the value? This one, t is equal to what? Small t is equal to infinity, na? So if small t is equal to infinity, so this term will be what? 0. So 1 minus 0 will be 1. So 1, okay, 1 multiplied by k, what is the value of k? 10. So at infinity, your value of response will be 10. So it will reach to the 10 value. But before that one itself, okay, so your system is reaching to the desired value in 7 seconds. From this graph, you can say that within 7 seconds, it is reaching to the desired value. Okay. I hope that you have understood this one.
Yes, sir.
Okay. Now, how this response depends upon time constant and gain, system gain, that we are going to study. Now, see here, see the system takes 5 time constant to reach its final value. Okay. Now, see that this is when t is equal to capital T, it reaches to 63.2% of its value. When t is equal to 2t, it reaches to 86.5%. And then when t is equal to 5t, it reaches 99.3%. So pleasant system is reaching within 5 seconds or like that. Now, see that see that this is the response of first order system for step input. This is the equation, say, of t is equal to k into e raised to minus t by t. Now we are basically putting the value of t, this time constant different, and k is kept constant. Now k is kept constant, and we are changing the value of time constant. Gain is constant here now, and time constant is changed. So when t is 1 second, at that time it is the response of that system is represented by blue line, right? So when t is equal to 1 second, means time constant is less, it is reaching quickly to the desired value, right? It is taking hardly, okay, within 2-3 seconds, it is reaching to the desired value. As t goes on, this time constant goes on increasing from 1 to 3, you have increased the time constant, so your system becomes sluggish. So it takes a lot of time to reach the desired value. Again, further, if you increase the value of time constant, like 5 seconds, your system will be more sluggish, or it will take a lot of time, like for example 7 seconds and so on. When t is equal to 7 seconds, it will take more than 15 seconds or 20 seconds to reach the final value. So what we can conclude is that if time constant of the system is small, then system will be faster. And if time constant of the system is large, your system will be slower, right? So this is the conclusion from this graph. I hope that you have understood from this graph. What is the conclusion? If time constant is small, it reaches to the desired value. What is the value here? Desired value 10. So it reaches desired value very quickly. As t goes on increasing, it takes a lot of time to reach the steady state value. Means when time constant is large, system becomes sluggish. And if time constant is small, system becomes faster. So this is the conclusion from this graph. I hope that you have understood this one.
Yes.
Okay. Now, here in this graph, we have kept gain constant and we changed the time constant from 1 second to 3 seconds, 3 seconds to 5 seconds, and so on. Now, in another graph, what we'll do, we'll keep this time constant same, and then we'll change the gain, and we'll see what is the effect of that system. Can you just tell me if you have understood this system? If gain is changed and if time constant remains same, what kind of graph you will get? Can somebody tell me?
suggest the peak value or the steady value will go increasing as the change.
Yeah, means basically, see, response time will remain same, na?
Yes, sir.
Response time will remain same. Only thing is that whether, okay, if k is equal to 1, it will reach to 1. If k is equal to 2, it will reach to 2. If k is equal to 5, it will reach to 5. And if k is equal to 10, it will reach to 10. Your response time will remain same. Only thing is that where to reach, whether to reach to 1 value, final value, or 2 value, 3 value, or 10 value. So this is decided by the gain. So see that this is the this one, where k is changed, gain is changed from 1, 3, 5, and 10. So it is reaching to the this one in the same time. So see that the time required for this one is this much, right, to reach the final value. Time required for reaching the final value remains same. Only thing is that where to reach. So when k is 1, it will reach to 1. If k is equal to 3, it will reach to 3. If k is equal to 5, it will reach to 5, and so on. So when you change the gain, your final value will change, response time will remain same. If you change the time constant, response basically time will change. So this is the conclusion from this graph. I hope that you have understood this one. Yes?
Yes, sir.
Okay. So this finishes our first order system. Okay. Second order system, we will start from our next lecture. And I think our next lecture, when is our next lecture? I'm not getting your voice.
The next Monday.
Next Monday. Okay. So next Monday is the lecture. Your exams will start from what?
From statement.
Okay. So